Good evening, ladies and gentlemen, and welcome to the 7th NUS Public Lecture hosted by NUS Cities. Before we start the event, just a gentle reminder to maybe turn off your phones or put them on silent. Thank you. For those of you who do not know about NUS Cities, we are a university-wide, multidisciplinary, open and inclusive collaborative platform hosted within the College of Design and Engineering, otherwise known as CDE. Through our collaborations with local and international institutions, we hope to create synergies within as well as beyond NUS. The NUS Cities Public Lecture Series will investigate policies, ideas, and projects developed by urban experts which aspire to create sustainable, resilient, and livable cities. Through the lecture series, we hope to create a platform for discussion, retrospection, and conversation to give momentum to the ongoing research and exploration regarding issues concerning cities. I would now like to introduce our first speaker of the evening. Prof. Jan Carmeliet is a full professor at the Chair of Building Physics at the Department of Mechanical Engineering at ETH Zurich, Switzerland since 2008. Prof. Jan graduated from KU Leuven and had been a professor since 1998, as well as a part-time professor at TU Eindhoven. His research have resulted in more than 330 scientific journal papers. His research interests concern urban climate and urban heat island mitigation, multi-scale behavior of porous materials and their fluid interactions, and multi-energy decentralized systems at buildings and urban scale. He was a research counselor of the National Science Foundation Switzerland and expert of the Swiss Innovation Agency, also known as INO-Swiss. He was also the director of the graduate program of Masters in Integrated Building Systems at ETH Zurich. He was a member of the Research Commission of ETH Zurich, the Scientific Commission of CCEM, otherwise known as Center of Competence, Energy and Mobility, and the Board of Energy Science Center at ETH Zurich. Please join me in welcoming him on stage.
Thank you very much for the kind introduction. You hear me? Yeah. So I will talk about how to model the urban climate, but first I want to give you some motivation. And maybe some of you who have been in Europe, we had the worst heat wave that we had until now is the one of 2003. And there we saw that we had an anomaly in temperature of more than 10 degrees. And the result of that was that there was a high excess mortality in France, which is estimated of more than 70,000 people. Now, this is excess mortality, so these are people that would not have died if there was no heat wave. So they really died directly caused by the heat wave. One of the reasons, of course, is that in France at that moment, they had no active cooling, even not in hospitals. So because traditionally, in residential buildings, we have passive cooling. We have, of course, active heating, but passive cooling. Recently, there was a study in Europe again in July 2022, and there they registered 53,000 dead people directly related to the heat wave, the hot month there were several heat waves in July. This is 16% more deaths than usual. And in Spain, it was even worse. It was 37%. If you put it in perspective to COVID-19, in July 2020, it was 3% excess mortality, and in July 2021, 6% excess mortality. Of course, COVID lasted much longer, so we compare just. But it means that heat waves or heat stress or heat exposure to people is really a killer, a hidden killer. So we are not totally aware of that. So I will sometimes go back to the IPCC 6 assessment report and take a sentence out of it, just to say somewhere to say how what we are doing is related to the IPCC studies. So recent changes in the climate are widespread, rapid, and intensifying, and they are unprecedented in 1,000 years. What is now the origin of one of the origins of a heat wave? It is that you have a high pressure system which creates a heat dome. So you have hot air that wants to go up due to buoyancy, but it starts to recirculate, and by that it heats up all the time. And so one of these examples of 2023 was the heat dome in the US. Let's go to Zurich. And if you look at the touristic info, it will say it's a climate with no excessive heat. Nevertheless, we have also heat waves. Now, the definition of a heat wave in Zurich is that we have 3 consecutive days of temperatures higher than 30 degrees. And as you know, there are a lot of different definitions of heat wave. It depends really of what people are normally exposed to, what is the normal climate. So in Switzerland, we find 3 hot days, an extreme. And as you know, there's a difference between the climate in the rural environment and in the city, and that we call the urban heat island effect, and the temperature difference is the urban heat island intensity. So we studied for the last 20 years. We did not study from 21 to 23, we should do that, but we found more than 30 heat waves. And you see here the same picture as I shown before, the same image, and you see that those heat waves are quite different. We very recently did an extreme analysis, and we looked also at how those heat waves are repeated. And for instance, if you take a 2-year return period, you already have a quite extreme heat wave. So it means you have quite short return periods of extreme heat waves. Recently, we introduced not a new concept, but the cooling degree hours is a concept that exists already for long years, but we use it also to characterize heat waves. And so what you do is you integrate above a certain base temperature, the air temperature that has been measured or modeled, and you integrate it over time. So it's a cumulative number. And we did that for the last 30 years in different cities. You see here Zurich. First of all, this is the yearly cooling degree hours. And you see a quite big scatter. So you have really hot years, you have cooler years. Now, if you look at the trend, you see that over the 30 years, there's an increase of almost doubling of this cooling degree hours, which is related to the heat exposure and also to eventually cooling energy. And in the rural area, you see that the slope is less. And this is something very characteristic. We see that the trend, the increase in cities is faster than in the rural area. We did this for different cities. Montreal, you see an increase of 68%, rural area 46%. Chicago, you see it's almost parallel. This has a lot to do because it's very close to a lake. And the rural area is not cooled by the lake, and by that is also quite hot. So there you see the trend is almost parallel to each other. We also looked at Sydney. What you see is that all over the world, even for different climates, the increase somewhere is very universal. It's somewhere between 70 to 100%, and the rural area is less. So that means that urban planning can make a very significant difference in urban heat exposure, and cities are crucial for both mitigation and adaptation. That you can read in the IPCC report. If I look at that, and I look at the picture again for Zurich here, that means if I want to mitigate, the green arrow is somewhere the maximum. I cannot mitigate more than going from this curve to the surrounding rural area. So it's a very easy method to see how much you can mitigate. And that, if you relate that again to temperatures, it means you cannot mitigate more than 2 to 4 degrees maximum. But that means you should then replace completely the city by a rural environment, which is impossible. So that means the mitigation is limited. That's why a lot of cities also do heat wave adaptation here for Athens. And this is measures like you have to keep the shutters closed all day. You should not keep small children and elderly people in hot places like cars. You should go in the shade. You should drink enough. You should work only during the cool hours, not during the hot hours, and so on. So these are measures that can be given to introduce a change in lifestyle of people. Or you can also have, like here in Toronto, in Canada, if you think it's very cold in Canada, it can be also very hot. So you have emergency cooling centers. That means that people that are suffering of heat excess have the possibility to go to a cooled place. So if, for instance, you have a building which is exposed a lot to heat, most of the time they say the best is to stay inside, but it can be that your house is heating up too much, so you can go to a cooling center. Now, again, what you see in the 6th assessment report, or it is by, it was a guest lecture by somebody of the IPCC, and she was saying that lifestyle changes can make a large difference, but if these are isolated individual actions, it's only 5%. So now there's a lot of pressure on us to dim the lights, to not take the plane and whatever. But if this is not systematic, it is just a droplet on a hot plate. It's less than, or it's 5%. But if there's a systematic change, then it can be 40 to 70%, but this is on condition that it is easy, attractive, and affordable. So, for instance, if you are on a diet, you know how difficult it is to do a diet. The same seems to be to adapt to heat waves. It takes a long, long time to change your lifestyle. Good. So that means that our future will be mitigation, adaptation, and suffering. And a lot of people say, yeah, climate is changing. We cannot change it anymore, but we can still change the mix on what we have to do. How much will we mitigate? How much will we adapt? And the more you mitigate and adapt, the less you will suffer. Okay? And there are a lot of mitigation measures that you can implement for cities. I'll give you here an overview. I will come back to those more in detail. But you see there's a lot of vegetation. There's also reflective roofs, constructive shade. Also insulation can be a good measure. And of course, efficient cooling techniques. So what I want to propose here today is that if you want to study the urban climate, you have to use a multiscale approach. That means you should start from mesoscale, and which has a domain size of 200 kilometers, where the city is not really physically modeled, but it is parameterized. So you only model the effects of the city. You can then go to a scale in between, what we call the neighborhood scale, where we start to use CFD, computational fluid dynamics, and finally we go to the local scale, where we start to model everything in more detail, as well air movements, heat transport, moisture transport, vegetation, trees, and so on. Let me first start with the mesoscale. What we use there are meteorological models. They exist, okay? So they go from a general circulation model down to the regional climate weather models where the weather is predicted. Now, those models don't model the city, or at this moment, they are modeled in a very rough way. And so what we do is we try to model those cities or the effect of the cities on the climate in a much more accurate way. And these are called, for instance, one of the models are double canyon effect parameterization model or urban canopy models. There are several of them, and they are still developing. What you do then is you use this meteorological model, you introduce the city, and you downscale. So we go from a scale, for instance, of a grid size of 10 kilometers, we go down to a grid size, sorry, I pushed too fast. We go to a size down to 250 meters. So D3, the domain 3, has a grid size of 250 meters. It means it's still quite coarse, okay? You don't see yet the individual buildings. And here you see a simulation of the heat wave in Zurich. We are now during the night. You see the hour. They're changing. Now we go in the first day of the heat wave, and we go to temperatures of around or above 30 degrees. Then it cools down again during the night. You see clearly the city. You see also the lake, the surrounding mountains, which are always cooler than the city. So now we go to the hot day where you go up to more than 36, and the third day, we even go up to 39 degrees. Good. With those simulations, now you can start to study what is really happening. And I showed here in this image really the resolution of 250 by 250 meters. And you see some hotspots. You see, for instance, the hotspot of the railway station. And why it's a hotspot? Because there's not a lot of vegetation. And you have the tracks, the railway tracks, which absorb a lot of heat. And then if you go to the lake or the surrounding of the lake, of course, it's cooler. Again, now we can use these cooling degree hours. What we used before on measurements, we use now on the simulation results. And now, of course, we can make a map of the complete city. And so here at the left, you see the complete map of the cooling degree hours for the June-July period 2019, and you see a lot of quite hot spots where the cooling degree hours is almost 100% more than in the surrounding. Zurich is let's say a small city, but it has a big agglomeration, and you see in all the valleys you have a lot of buildings, as you see here on the right, and so all where you have a high density, where a lot of people live, you have the high cooling degree hours. So this is a quite interesting technique to identify where in your city you have hotspots, and also to try to understand why there is a hotspot there. And for that you can do heat flux, heat flow analysis. And I don't go in the complete details of this equation. There should be a lot of other terms, but you can say easily how much heat is stored in the ground or in the buildings is equal to the net incoming radiation. So you have solar radiation coming in, you have some reflections and whatever, and you have also long wave radiation going up to the sky. Minus the sensible heat and the latent heat. Latent heat is due to a phase change. If you go from liquid to vapor, it needs energy, so you have an energy that you need for that. So this is called latent heat. And you can make a map of Zurich of the sensible heat flux during the day. So the buildings have been heated up. So there's a lot, by convection, a lot of heat coming from those buildings, which will heat up the air. You see that also you have quite some latent heat flux because, of course, the vegetation is active. During the night, latent heat is zero because trees don't transpire anymore. And you see also during the night that the sensible heat flux is much lower, which is good, beneficial, because we want to sleep, but it is not zero, not really zero. You can then make the difference and determine the heat storage. And you see that the heat storage during the day is positive. This is because solar radiation is really stored or absorbed by buildings, roads, and so on. And during the night, you see it's negative because you have long wave radiation mainly, and also some sensible heat. You see also that there's a difference. During the night, it's higher than, during the day, the gain is higher than the loss. So it means my city at this moment is heating up. We studied for Zurich different sites, hotter ones and cooler ones. And we looked at a special heat wave. We look especially at the red zone where you have temperatures above 30 degrees. But also what is important to see is that in the period before the heat wave, classically, very typically, you have a ramping up of the air temperature. And the question, of course, is how does this happen? What is the reason for that? And so you study for these 6 places, you study the net incoming radiation. It's all the same, almost, okay? So the radiation balance is quite the same. Sensible heat, of course, there are some differences, but you see in latent heat, there's quite some difference. And you see in the uphill on the mountains, you see a very high latent heat. Then you have the lakeside and the park in between, and then the city downtown is quite not a lot of latent heat. And that, if you just calculate this heat balance, you see almost the same trend as the air temperature. So this storage means the ramping up of the storage explains why the air temperature is increasing. It's because you store more heat than you can lose, and this is very typical for heat waves, that there's an imbalance between the two. Let me go now to Geneva. It's also a city at the lake, so very typically in Switzerland, most of the cities are at the lake. And you see here land surface temperatures that have been measured over 3 years, and we only selected those measured temperatures that where there were not too many clouds. Okay, and so you get a map which I could say is quite typical, showing where you have the highest surface temperatures. And somewhere you can start to try to relate those measured surfaces with land use, where you have buildings, where you have less vegetation, you will have higher surface temperatures and so on. Now, with the model I presented you, the mesoscale model, you can also model the air temperatures as I already have shown you here for a heat wave in 2019. Not only the air temperature, you can also start to calculate some variables which are very important for the comfort, the thermal comfort, which is not only the air temperature, but also what we call the mean radiative temperature. It's a little bit too complex to explain, but it means how much from sky surfaces, hot surfaces, you get, and from the sun, you get radiation, averaged out. And then, of course, humidity is important and wind. And so, for instance, here we calculated the mean radiant temperature. And you see again that you have the city center here, which is quite hot. And then you have some hot regions also where you get quite some radiation. And then you can combine these results with the physiological model. Also, you can say how much clothes you wear. And you can calculate what we call the UTCI, which is the Universal Thermal Comfort Index. And what you see is when it is above 26, we say there is a heat stress, moderate to extreme when it's higher than 46. So we calculated also this UTCI, and you see that we get quite some high values up to 40. 40 will says very strong heat stress. Of course, this is at 4 p.m. This is the worst moment of the day. Good. Again, we can say, let's look over longer time. The cumulative effect, it's not only at 4 p.m. I'm exposed maybe several days. So we looked at the thermal discomfort hours. So all the UTCI temperatures that are above 26, we accumulate over time, and we just plot. And you clearly see there are some hot spots which somewhere relate also with the higher surface temperatures. So this means that with this method, this mesoscale model, you can do quite a lot. You can identify where are hot spots in your city, and you can also try to understand the global heat balance. Now, to our opinion, those models are not sufficient to go to design mitigation levels at local scale. So for that, we go to the lower scale, and we try to understand what are the effects of trees, and we try to model all the physics included. So we developed over the last 15 years a method which is CFD based. So we solve for the turbulent airflow due to wind and buoyancy, radiation balance using a view factor approach. We also, and I think this is quite unique, what we do, we also look at heat and moisture storage in porous materials, including phase change. So you can calculate the effect of evaporative cooling. There's glass, trees are also included. And eventually, if you like, you can also turn on the wind-driven rain module. I give you one example. You see, this is the local scale. It's a square in Zurich, Münsterhof. Münsterhof means that there was a monastery, and the monastery became a square, and you see the square is totally mineral. There are no trees. There's a little bit of water, but that's, of course, very small. And so this place is known to be quite hot. And so there was an interest of the city of Zurich to understand and see eventually if there are some mitigation measures. This is the setup. We start from a mesoscale model. We take the boundary conditions there, and we implement them in a quite big domain. And we model only a part in the middle where we solve, only in the blue domain, we solve the complete model, everything. Heat, mass, transport, including evaporative cooling. In the bigger domain, the green domain, we only solve the heat balance. Good. And we looked at a heat wave in 2019, especially we analyze more days, but I focused mainly, or I give you the results of June 25th. And we looked at two solutions, two mitigation measures. One is that we introduced porous pavement that, of course, you have to irrigate, you have to wet. And we studied a lot on when you should wet and how much you should wet. We find out that with 6 millimeter between 8 and 820, you have the optimal effect of cooling. And we also looked at adding some trees. Of course, it's a square, it's a public square. You cannot put it full of trees. So that's what the urban designer allowed us to study. And you see here the simulation. On top, you see the air temperature, bottom, the wind speed. We are going now over the day. This is the river, the Limmat River. And you see there is quite some flow over the river, which is a ventilation corridor. And sometimes you see also there's some wind going from the river into the square. Of course, it's quite limited. And you see also that the temperatures change over time and can become quite hot. So one of the questions that are asked a lot is, how much do trees block the wind? And I give you here an example. At the same time, without trees, you see that there's a lot of circulation of wind coming from the river, the Limmat River. When you add some trees, of course, the blue zones extend, and you have quite some zones where you have less wind. Also, what we see is that the complete three-dimensional structure of the wind can change completely by adding trees. So also the heat removal by wind can change quite a lot. I show you here the surface temperatures over the day. You see the hot spots that are the hot temperatures, which are up to 50 degrees surface temperature. And of course, you see that here, due to shadowing, these hot zones are much less developed. You can then calculate over which zone the air temperature is reduced due to your mitigation measure. And you see here at 12 UTC, is universal temperature in Europe. Time in Europe. You see this is around 2 o'clock here in the afternoon in Zurich. You see that there's quite a big volume that has a lower temperature due to trees, and Dominique will explain much more in detail why this happens, but the main reason is, of course, you have wind flowing through the tree, and the tree, by transpirative cooling, is cooling down the air. If you compare that to the evaporative cooling effect, you see this is much more limited because, of course, this is a surface effect. It's not the influence on the air temperature is much more limited. Of course, it's efficient, but what we say is if you want to use evaporative cooling pavements as a mitigation measure, you should combine it with shadowing also. You should not only count on evaporative cooling. And you can calculate the UTCI, and you can see here how you can go from very strong heat stress to strong heat stress. And what is important to see is that you get some places where people can walk. And so if you want to cross this square, in the case with no trees, you will suffer. Okay, then you go in a street which is cooler because there's shadow. So, but we want to make cities where you can walk, where people during heat waves do not just have to stay inside, but they can still go outside. And you see with trees, you can make pathways where people can pass through and go through the city. We looked also at another place in Zurich, a little bit bigger, where we had a lot of trees. And the question of Zurich was, what happens if I put there some higher buildings? These are not buildings like here in Singapore, they are only 60 meters high. What you should know is that wind flow is important. And so those high buildings will, of course, block the wind, but you will also have a downflow. So you have a lot of air that is blocked and will go down and then go around the building. And this is what we call corner streams, which in winter, when it's cold, you don't like those corner streams at all. So we did a calculation here at 3 time slots, the existing situation. And what you clearly see is that, yeah, those trees really cool down locally, but also the building. The shadow of the building will make that there you have better comfort. So now the question is, what happens if you put there a high building? And what you see here is that compared to the zone there, you have a much better comfort at the crossroads. The reason there is shadowing, of course, but also this cool wind that comes down. It can be also, of course, if you have inversion, that you can also have hot wind coming down. So it is not always so easy. Last example that I show is the night cooling potential during night. And you see here the current situation, and you see also the wind coming from the bottom, but you see how complex the wind pattern is. And I have to say you, it will change all the time. And we studied really the influence of the wind flow on the local temperature. You have to remember this is during the night. In Switzerland, we say if the temperature is below 26, you can sleep comfortable. Is it above 26? It's not comfortable. You see some places here during the night where you have really temperatures above 26. Now, one of the reasons why you have a quite good climate here is that you have a lot of cold air coming from the mountains into this street. Now, they asked us what happens if you densify, and I show you here the case, the current situation, and here where you densify. So especially here are some higher buildings, but also you see there's more buildings around the street. And you see that the red zone here is quite different than there. The pattern is different. The reason is, if I show you here the airflow, here you have really the flow through the street. And if now I densify, you see that this high building here will deflect the wind. And so the wind will go here and then go up instead of going straight. And that explains why you have here a hotspot. So that means that high-rise buildings don't change only the neighborhood close to it, but can also upstreams and downstreams, it can change the situation. So I come to the conclusions. There are a lot of possible solutions. Vegetation is one of the solutions. Dominique will tell more on how it works. I just say we still don't know really how it works, when it works well, when it does not work so good, because of course you have different species of trees, you have different planting patterns, you can have green facades, green roofs, green parks, green shading, and you should take into account, of course, the size of the tree, but also the growth of the trees. Yes, it takes time. If you want to make urban forest, it will take time. You should also take into account the urban water cycle. In some cities, you can have quite some hot, dry periods, and of course, then trees could be that they close their stomata and they will not work. The building morphology can have a big impact on the efficiency of a tree, and opposite, and the background climate. Of course, a tree will act differently here in Singapore as in Zurich. We are looking at new solutions, bio-inspired solutions. I will not go too much in the details here, but this should make that the disadvantages of a tree can be replaced by some shading devices which are intelligent. You can also think as green balconies, urban farming, and so on. So I come back to these mitigation measures. How should you select them? I think you should not select one. You should select a set of mitigation measures and then see what is the impact on the comfort and the health. You should also look how much time it takes to implement them. Are those different mitigation measures compatible? How much do they cost? Are those mitigation measures also accessible to all people, also the poor people? It is known that in a lot of cities, the hotspots are in those parts of the city where also a lot of poor people live. And one of the reasons is there's less investment in trees and vegetation in those neighborhoods. Acceptability and so on. We did once a study asking 30 experts how they would classify the solutions, what are the best solutions for a certain site. And you see we had a lot of solutions where the best one was reflective roofs, insulated envelopes, evaporative pavements, and constructive shade. But there are quite a lot of other possibilities, of course. We should, of course, implement a roadmap how to do this over time. Now it is here until 2030, because in Europe, for 2030, a lot of cities should have reached their target, which they will not do, of course. And I think it's very important not only to look at the microclimate, but also look at all the co-benefits. Biodiversity, if you implement different vegetation solutions, you increase, of course, the biodiversity. You increase not only the health and the comfort, but also the well-being, even not during heat waves, okay? You have, of course, an impact on building energy and other energy aspects. You can include, when you look at mitigation, to the decarbonization and also to the resilience. And I come then to my conclusions. I think I made it clear that our cities are heating up. Whatever measures we take on big scale, for the next 50, maybe 100 years, we will have an increase of temperatures in our cities. And so we have still time to choose between mitigation, adaptation, or suffering. I think we have to do these mitigation measures on short and long term. I showed you that with the multiscale approach, which is mainly a downscaling approach, from meso to microscale, using physical models. Well, I'm very sure somebody will say, yeah, but I do it with machine learning. Of course, but you have to train your machine learning. And so you need accurate data, and those can be created by those physical models. And finally, we should couple urban climate to building physics, what I started with building physics originally. And we should, I think, also still look at the design of adequate passive and free cooling systems. And with that, I thank you for your attention.
Thank you, Professor, for that very interesting lecture. In the interest of time, can we take maybe only a 5-minute break, and then we come back for Prof. Dominic's lecture? So it's 7:10. We'll start the second lecture at 7:15. Thank you. Welcome back, everyone. I would now like to introduce our second speaker for the evening. Prof. Dominique Derome is a professor at the Department of Civil and Building Engineering, Université de Sherbrooke, Canada, and holds a Canada Research Chair Tier 1 in multiscale building physics. She looks at heat and mass transfer processes in the built environment, the related impacts on durability of materials, namely wood, and on thermal comfort and its inhabitants. Her research proposes innovative and multiscale approaches of the highly coupled physical processes that occur in the built environment, intensively integrating advanced computational and experimental methods. This multidisciplinary research leads to solutions developed for a sustainable living environment, resilient in the face of climate change, possible higher risk of heat waves and impacts on the urban environment. Her research has led to more than 180 journal papers. Previously, she worked for 11 years as a senior scientist in Switzerland and 10 years as a professor at Concordia University, Canada. She's also the editor-in-chief of the Journal of Building Physics. Please join me in welcoming her on stage.
Thank you. So thanks for the invitation. Thanks for the introduction. I'm very happy to be here and complement the presentation of Jan. What we have done a lot in the last 8 years is to include trees in the urban environment. Trees are always expected to be the solution, the miracle solution for cities. Of course, we know trees are very, very helpful, but there was no way to know how much by how much. There was no quantitative way to understand what was the role of trees. We did not plan to look at that, so to have to develop. We wanted to use a tool, and there was nothing. So it did not exist, so we had to make it. So what happens is that we have a responsibility as people from building physics to bring our knowledge of buildings to the urban environment, because we understand so many things at the beginning scales that we could go to the urban scale and bring all of that. One of the things we had developed was rain deposition, so wind-driven rain deposition. When we did that, we had the CFD code that we put rain, and then we had this environment where we said, okay, we can add more, we add radiation. In buildings, you always have porous materials, so we had the porous material, heat and mass transport, but trees, there was a big adventure, a long adventure. So Jan explained the general framework. I will just look at what we do in microscale urban modeling, just considering vegetation, and showing what we can do to look at different mitigation scenarios, or what type of information we can get with this type of very explicit modeling in terms of information or insight on what happens in cities. So this is what we are using. So if we implemented in OpenFOAM, we use the CFD capacities of OpenFOAM. We implemented in OpenFOAM wind-driven rain, and then we added radiation, so all the short waves, so from the sun and all the exchanges. Then we had all the porous material. And in each of those three models that are coupled, we have to take into account trees. So in the air, we have to make that the flow through the air, through the foliage, that we have to look at solar radiation, what is the surface temperature of the foliage and the exchange with all the other surfaces. And then, is there any transport in the trees that we have to consider or not? This is where we had to say, so depending on the problem, we can consider a full tree. So the tree is a foliage, it's a structure that supports foliage, which has different shape. The leaves can have different shapes, the foliage density can have different shapes, the tree can have different shapes, the trunk can have, the root, everything can be very, very varied depending on species. And then we have to consider that a lot of information is unknown, so all the root system is unknown. Almost no information exists on the root system of big trees, where they get the water. The trunk is quite understood, how water goes through the trunk, how it gets to the leaves, that's all quite understood. actually in all the exchanges of heat and mass with the air depends on a lot of different parameters of the leaves. So when we consider now in what I will show, we will say, okay, we will consider that the roots are in connection with water, and we will not model the roots here. We don't need it, okay? So if a tree is really well established and is all green, it's because it has connection to water somehow. And most of the trees that are established found some kind of underground river or some sewers, and they get water from there. Street trees, it's difficult for me to say that, street trees don't have a lot of water that comes from the rain because it's almost all sidewalk and impervious surfaces. So let's say that if we know that we take for granted that the tree has access to water in the soil, we don't need also to the transport through the trunk to the foliage. But we can do it if we want, because we come from building and we do heat and mass transport in wood, in building for other applications. So we could have it here, but we don't do it here now, but we have the foliage. And what is the foliage? It's not just a big unknown. It's made of leaves, and each of the leaves has the capacity to make it to be a photosynthesis site. So the leaves have chlorophyll sites that receive the energy of the sun and transform it with CO2 into sugars, and the sugars will build up more of the tree. To do that, you need water. So the tree from the root all the way to the leaves is just a column of water in tension and brings the water for photosynthesis. If you have sun on the leaf, you need to have water to make sure there's water in continuous way. The tree will open openings underneath, and it's called stoma, and all the stoma together, the plural of stoma is stomata. So all the stomata of the leaves will open, making sure that you have evaporation, pulling all the water, and this is 90% of the water that will result in 90% of this water to leave the leaves, and not be used by photosynthesis. So it's not efficient for the tree, but that's the balance they got through their system. What is good for us is that it means that 90% of this water goes from liquid to gas. There's a phase change, so you need energy. So all the leaves that undergo photosynthesis and evapotranspiration, they get cooler. The surface gets colder by a few degrees. This means that if you have a cold plate, you have wind that goes above that, you can exchange, and then you can cool down the air that goes through the foliage. So this is the source of cooling that we have in the tree, and we can reproduce that by taking into account that if the leaf of our tree is exposed to solar radiation and there is enough water in the soil that brings that there's enough water at the site of the photosynthesis, we have photosynthesis, we have evapotranspirative cooling, and this is what we put in this code, taking into account all the exchanges in terms of convective exchanges at the surface. The stomatal resistance, when it's closed or it's open, we can calculate that. We can calculate how much radiation gets on the surface, if there's a lot of leaves or not, and then get all of that as a heat balance at the leaf level. Now we have, into our system, we have this leaf model that we distribute over the volume, and there we can just, in our CFD, take into account the impact of the presence of foliage, and have into all the equations take into account the drag aspect and the humidity generation and the heat exchange due to the leaf in terms of the CFD. Solar radiation means what? It means that the sun comes through the foliage. There we do just an extension to the foliage. And then we have to do that just technically. We have to shift the grids depending where is the sun. So during all the day, we always shift this extension grid to not the CFD grid, just the grid calculation of direct of the shortwave radiation. All the surfaces of the tree, now we have the long wave radiative exchanges, so surface to surface. So here you see that the surface is kind of flat surfaces, so we had to minimize the number of surfaces, because if you take a perfect round shape, you have too many surfaces to do all these view factors, it became crazy. So now you will see how we optimize the shape. And now we just have this view factor calculation of all the exchanges. We put that into all the CFD normal way to make the domain with the proper ways to do the domain. Jan explained that we can also do inside, you can use a WRF or a mesoscale model to do all the boundary the input conditions at the boundary of our domain. So now we have this system in CFD. All the air and the solid are coupled. So we exchange information between all the air domain and porous materials. So we have heat and mass exchange at all the surfaces. This is where we have all the boundary information from mesoscale. We are set. And then we can take this information and know everywhere in our domain what is the air temperature, what is the surface temperature, the velocity of the air, the relative humidity of the air. And then from the surface temperature, we can get the MRT. Then with this information, we can put that together into a thermal convert. And here you go from a surface temperature result into a UTCI result. So you see that if you're under the tree, it's more comfortable. And you really needed my model to understand this, okay? I'm sure nobody would have understood that by himself, okay? So, but it just shows that it is a way to be quantitative, okay? And then you can start to see, okay, now we can look at what is the impact of the tree everywhere, or we can also compare solutions. So this is not absolute temperatures, just for those who don't know thermal comfort index. This is a perception of the feeling, and then from that you can say if the person is a way of he's stressed, and then when you know that, you can give that to doctors, and doctors can do something with that. Doctors don't know what to do with that because they know it's a heat stress, but you cannot accumulate heat stress yet. Okay, so this is still a big need that we have, is that to how we go from instantaneous heat stress to, at the end of the day, the cumulative heat stress, and what is the impact of health. So this is not what we do. But when the doctors will tell us what we can do, we can use it in the model. So now, a few examples. We looked a lot at different trees to say what is the best way to look at the configuration of trees. We took LiDARs of trees. We used different species in Montreal, different age, looking at the foliage, the size, and see what is the best way to look at that, because we did a lot of trees like this. Why we did that? Because in CFD, it's very easy to do this, okay? So that's what we did. Of course, you would be tempted to do this, but this means that you have so many surfaces, like it's like the view factor becomes crazy. So this is just if you do LiDAR, you can wrap your volume, but it's still a lot of surfaces. And we came up with this shape here, which is the rhombi hydro, it's on the next page. Get the name, it's RBO. Okay, so it's the type of geometry where you can stretch it and get, so, and if you compare, this is the UTCI on all those trees that are not impossible, and compare with our tree like that, we can get the best representation of trees. If you compare with the exact LiDAR and the simplified rhombi cubo autohedron, which I found the shape. I should know the name, but I cannot. Okay, so you get very, very good representation. What is nice is that you can move those vertices and come up with any shape of tree, and you don't have so many surfaces at the end to calculate. And that was very good to optimize our different shape of tree, and that's what we almost always do now in terms of shape of trees. So now we have a neighborhood. We put a few trees, a small study here to show that what is the impact of the age of tree because you plant a tree, it takes some time before the impact. So here are the surfaces, the temperature of the surface at the bottom of the tree, of trees of different age, okay? And now, if you combine this, you see, at the end, you will see that it takes really some time before you get to have a big effect of the environment, on the environment from trees. So you really need to wait 20, 40 years before you start to have a tree that has a real impact on the environment. Because if you look, the gray is no tree, and then those two red here, they don't have a big impact, okay? Most trees in Montreal, I don't know Singapore, when they are planted, they are between 5 and 7 years old. They are for like a few centimeters in diameter of trunk, and half of the trees die within 5 years, because it's very difficult to establish your root system and to survive. So it's very difficult to get mature trees in the cities. But once you get it, you can have very big benefits. So you have to think long term. So now, if we want to mitigate the climate what we do now, will have an impact in 20 years, 30 years. You will all be grandmother and grandfather, okay? Not only me. So it is really a way of thinking that we have to decide things now, but it's not so easy, because you have to say where we put the trees, how many trees I put, which species. So there are still questions to look, so that we look at here as one example. So this is the traditional way Montreal is built. It's really those lots that are very rectangular. This is a normal street with trees. And then we see, okay, how we can optimize where we put the trees. You can look at, here, this is the computational domain. We can look at heat wave days, for example. We can look at what's the impact at different places in this system. And then we have this capacity to look either globally, what is the total impact all over our site, an average, or we can really decide what is the impact in a small street, in front of the door of the people, on the balcony, in the courtyard, and look at to a level of information in terms of surface temperature, UTCI, like thermal comfort, change of what is positive, what is negative. Wind is slower because of the tree. The leaves, they evaporate, so we have higher relative humidity. So you have two negative aspects of the trees, but you have solar shading, and you have evapotranspirative cooling. So is there sometimes where the negative impact of trees are stronger than the positive? Yes, at night we see that. But it's in the day, it's so good. So how we balance, how we decide, this is still to be done. Okay, of course, you have landscape architects that know intuitively a lot about how to use trees, okay? So I'm not denying that. I'm just saying that we would like to have more precise answers and give real guidance to all those that don't have this intuition. So then we have this simulation here. It's like so for the whole domain, what is the impact of where in terms of the relative, here is just in terms of temperature, surface temperature, air temperature you can look, and then we can see, okay, here again, this is, we put almost no trees, just in the courtyards, we put some trees. And does it have an impact? So why we do that here is because in the streets are full. Under the sidewalk, it's full of pipes and stuff and phone cable and everything. So if you want to add more trees, it's not the best place or the easiest place is in the private courtyard. If you can show that private courtyard trees have also an impact on the street, you could maybe motivate people to do more. And this is what we show here. So of course, in the courtyard, this is where you have the most impact, but you still have impact in the small roads, okay? And then this is the type of information that cities are really interested to. Also, people developing ecosystemic evaluation of all the surfaces of the trees. It's part of that. So here we can further and see, okay, if we have one system and we look at which component of the UTCI has the most impact, you see that here it is so the solar radiation, or the yellow line is for the radiative exchange. This is where the tree have a big impact, of course, because you with shading you have a big impact on solar radiation, but you can now measure it, and you see, and you can put the tree on different sides of the street, and see, okay, maybe that side of the street is in the shadow in the morning, you don't need the tree. Maybe it's where you put the tree, so you can continue to look into more optimized way of deciding where you put your trees. And then you can also look at the difference in UTCI. So what it makes that, so without this solution, how much of UTCI locally you have in different. So this is, you see here that the green line at night is above zero. So here it's negative compared to our reference case for this problem. It doesn't mean it's always negative, but you can compare solutions with that. And this is all the different solutions. You can compare the relative effect at night, when it's below zero, here it's a negative impact, and the impact in the day is positive. You can compare solution, you can compare where you are in the street. So this is the example that Jan has presented, but you can see now we can look at big domains so you can put many trees in this domain. So here the buildings don't have the same, they are simplified geometry, but you can look at like hundreds of buildings, hundreds of trees together with this model. And then you can look at, even though, so you have so many trees here, you can look at the impact of changing the foliage density, which means what? It means you change the type of tree species. And this you can really see if you go from different leaf density, you have a big impact in terms of the air temperature that you come out of the tree, because you have less or more leaves. So something similar to that. So here you see the impact of the LED. And then we looked at what if you have not only a few trees, but bundles of trees. So it's the trees that you find in parks. So here Jan showed you this park, this square in Zurich, and you saw how much big volume the trees provide. So it's a machine that is volumic, that it's a 3D machine, the trees. It has an impact on a big volume. It's so different from many other solutions that are considered when we look at water pond or pavement, like white roofs and all that, which are just surface. Here the tree is working, is distributed in space. So it's a tool that we don't have. There's not a lot of other tools that have this capacity to affect so much volume. So it's a nice, it shows it very clearly here. So this is a park. So Montreal Island is here. This is the South Shore. This is the St. Lawrence River. We have a park in the middle of the river. It's where we have the Formula One competition in race. I don't know how you say that for cars. So the Formula race in Montreal. So when I was little, I was living here, and you could hear the car. You did not need to put the TV on. You heard the cars the same level as okay, so it's really very good from the environment, almost no use of fuel and anything. But so this is here on this island. This island here is St. Helene. This St. Helene Island was the object of a retrofit, and they had 2 parkings, and they want to say, we would like to make it green, and because those 2 parkings there, we will just make that people have a local little train that they don't need to come with cars, and we will make it that we don't have this local heat island in the park. So now we can use the same modeling suite to have the island in the river, so we can have the temperature of the river, the temperature of the island. We have those 2 parking places that we will replace with grass and with trees, and we have made a wharf simulation for Montreal so that we can know what are the boundary conditions. And this is the domain of the wharf simulation that we did. We take a few days that are about the heat wave, because we want to look at the impact of trees when it's the hottest days. Okay, no, here we did not. This is not the hottest day. This is the comparison. This is the comparison at one time of the wharf day with the measurements that we had. Okay, so this is the way to show that our wharf day was useful for our site. And then we use warm days to do the simulation. So this is a WRF result to show, and then you can see the surface temperature at one point. Then we put that on our domain, we simulate, and we look at what is the actual situation in the actual park. So this is the vegetation as is. There's a small building here. Actually, it's the building of the swimming pool where people can change this. There's a little forest here, a little patch of trees, and then trees. And then we can look at from this. So from this simulation, we can see where is the air after coming from the left here, when it comes to the forest, where it's cooled. Although the air temperature is 32 degrees, when it goes through this forest, it's cooled by 2 or 3 degrees over this volume here. So this is 3-degree cooling. So it's significant air temperature. So we can look at the exact impact, not only of a single tree, but of a big patch of tree. We can see what is the impact of the presence of trees on the velocity, the path of the velocity, and then what is the air temperature along those paths, in trying to understand where you position best the trees. We can also look at, and this is very nice, this is the volume of the forest, and these are the top leaves that have a super big sensible cooling density. And then this is like a level of leaf, another volume of leaf a bit lower, and this is in the middle of the trees. So you see where you get a lot of solar radiation, this is where you have the most activity of transpiration. And then you have here, you can look at what is the cooling power, the potential of cooling of all those. You see the big power has not a big volume, okay, because you have a big extension in the foliage, but you can quantify the tree in sub-volume, and then you can associate. We can also know from the simulation what is the temperature of the leaves everywhere. So here, the leaves are all the same. All those trees are the same characteristic of the leaves, but you can play with different leaves. You can play with different development length of the different trees, different stomatal resistance. I have more information, but this is here. If all the trees have the same type of leaves, we can see what is the temperature, where the leaves are cooler, where you can now have the impact of the forest in terms of cooling. And what we saw is that coming out of the forest here, we could see this 3-degree reduction of the air. And then we have all these little trees that also have impact. Of course, the little trees, it's not the same impact as a patch of forest. And then you can see, okay, but I have to add more. So if I replace this parking by grass, then I have to add some pieces. I cannot fill this by full. I cannot put full forest because they needed to have some activities for children. So it had to be sparse trees. And then we had the designers, the landscape architects, giving us different ways where they would want to put trees. And we could compare then after that those different solutions. So this is the base case. And this is here what is the UTCI everywhere at 2 o'clock, I believe. Okay, I did not write it, but it's 2 o'clock, I believe. And these are the different situations, the different scenarios. So you can compare what is a scenario in terms of UTCI, and you have it in a map. So you know, okay, here if I put the activities for the children here or there, okay, for the little ones, it's where I put the benches for the parents, and you can really look at what is the impact. Or you can also have it in a more generic way and say what is the average temperature and where is most. So you can have a tool to support decision, guide solution, understand more what you do, and then also do we have everything in our model? Well, we have shading and evapotranspiration. This is quite good. We can change a lot about the leaves information. We still need to do more in terms of configuration and look at all the possibility with the leaves. We use UTCI now as a tool. Jan talked a lot about cooling degree hours. Another tool to estimate the impact of different solutions is that there should be other ways to look at all this plus and minus of the trees or any other impact, okay? But at the end, what we want to give is first understand why we need a green infrastructure in the city. What is the impact? How we can quantify it? How we can sell to people that it's worthwhile to plant a tree now, although the effect is in 20 years. Okay, this is difficult. How you go to about that? And if you don't have effect only in 20 years, can you put with the tree other stuff, grass underneath, little plants, what you put, so that at least here you have some kind of mitigation until the tree is really big and provide all its services. So so this is what we have developed so far to try to understand more what the trees are doing. Of course, we are looking at other types of mitigation of the urban climate. That's not the only one. We are really, really adamant about explicit modeling, okay? So anybody that says it takes a lot of computer time, I say, so what? Because computer time, it's not your time. It's a computer that runs it. Although it takes some time, it doesn't take anything away from you. Okay, so of course, there are big simulation, but you get very good data. And once we have this very good data established, maybe we can produce after that other tools using machine learning and making things that can be easier to use. But so far, we don't have the physics to do that. We still need to produce the data. And explicit modeling has a big role to play in all of that. So I thank you to have listened to what we're trying to do in finding solutions to have cities that are more resilient using green infrastructure. Thank you.
Thank you, Prof, for that very inspiring lecture. I would now like to invite the moderator for the evening, Professor Yun Chao. Prof. Yun Chao is an associate professor with tenure at the Department of Architecture, National University of Singapore. He was the recipient of the Presidential Young Professorship when he was an assistant professor and is also the founder and principal investigator of Urban Climate Design Lab in NUS. Being an architect, urban climate researcher, and educator, Prof. Yun Chao's teaching and research focuses on climate-sensitive urban planning and design for sustainable and resilient cities. The topics cover urban wind environment, traffic-related and transboundary air pollution, anthropogenic heat, passive cooling technologies, and urban greenery. His goal is to support and develop practical planning and design in real life to build sustainability and resilient cities. Prof. Yun Chao currently leads his research team in collaboration with MIT and ETH Zurich to conduct several studies on urban climate and future resilience for high-density cities. He also serves as the Director of Research at NUS Cities, Associate Editor for Urban Climate, and Editorial Board Member at Landscape and Urban Plan. His work has been published in leading peer-reviewed scientific journals, book chapters, as well as self-authored book titled Urban Wind Environment, Integrated Climate-Sensitive Planning and Design by Springer Nature. Please join me in welcoming him and our two guest speakers for the Q&A sessions. I would now like to invite the audience here as well as on Zoom to raise their questions. There are ceiling mics, so you can easily just raise your hand and speak aloud. Yeah.
So how much time for the Q&A? Okay. So we have 40 minutes. Who want to ask the first question? I see a lot of friends here. Uh-huh. Oh, yes, we have the first question.
Eric Velasco from the Molina Center for Energy and Environment. I have two questions, comments for both speakers. The first is that all your findings are based on modeling studies. What about findings from field observations, including measurements of the thermal structure of the atmosphere, the production of turbulence, measurements of heat fluxes, etc.? That's the first question. The second one is that your results are very valid for mid-latitude cities. They may not be valid for tropical and subtropical cities where urban typologies and climates are different. For instance, trees in Canada and Switzerland are very different from trees in Singapore. You didn't talk about turfgrass, and turfgrass in mid-latitudes are mainly C3 species in the tropics, and subtropics are C4 species. That makes a difference, I guess. Secondly, we always talk about urban warming in a bad way. It may be true for mid-latitude cities, but in other cities it may not be. For instance, urbanization in the case of Mexico City has the opposite effect. During daytime, urbanization cools the ambient air. Thank you.
Okay, long question.
I will do the model that we have developed can take into account any type of trees or any type of climate. Of course, my observation or my conclusion here are for the climates and the trees that were studied, but there's nothing that prevents to do it for Singapore or to do it for other type of climate. So the modeling suite can do it. Any type of trees, any type of building, any type of climate. And then you have just to do the study, and then you get the observation specific for that.
So physics is physics, right?
Physics is physics, yeah, that works, yeah. You want to go on the observation?
Yeah, so on field observations, we presented here one kind of approach, right? But of course, other approaches are as valid and complementary. And every approach has advantages and disadvantages. So the disadvantages of field observations, of course, is that you don't get, depending on the technique, right? The time resolution and spatial resolution can be different, right? And so sometimes you have, with the LiDAR, you have a very good resolution in height and temperature, but not over complete cities. You cannot put hundreds of LiDAR, okay? So you get an information of different qualities, different resolutions. Time and spatial resolution by field observations. It can be cheap networks with low, cheap sensors having some information. So my belief, and I did not show the example, but what we do is we do mesoscale simulations, and then with a network of observations, we do machine learning, and we optimize our WRF simulations, right? So we correct our WRF simulations that we know have some errors, some time bias or whatever, with field observations.
And satellite.
And satellite, yeah. So I see it more as a hybrid approach. You do and simulations and observations, you combine them, and based on that, I'm very sure that we get more higher quality data. Of course, the advantage of simulation is that you get all your variables almost at any time resolution and spatial resolution you want. Disadvantage is you cannot simulate a complete year at this moment with what we have shown. That's only some days. So that's, now I find, my personal opinion is that a lot of people want now to have very fast models so that designers can immediately see the impact of changing whatever and so on. And that, of course, is good, and I have nothing against, but you cannot replace physical modeling and very advanced field measurements by those tools. That's a danger. And so I don't know if I answered your question. So yes, field measurements are very important and should not only be used as validation for models, it's also they give insights of what is really happening.
Yes, fully agree. Field observations and numerical simulations are complementary. And maybe I would add that data-driven methodologies could help us to solve additional questions.
Yes.
There is also the one thing is that when we develop something and we don't find in literature something to validate, we need to do our own experiments. So when we developed the wind-driven rain, we had to do our own field measurements to get measurements of rain deposition on different shape of buildings so that we could validate our model. So when you're an experimentalist, the way you look at the problem, you put the sensors and everything not in the same way as what we need when we need to validate a model. So when we, as modeler that know that we will use the data for validation, we don't have a campaign that is designed the same way as experimentalists. So of course, information from experimentalists is very useful. We can get a lot of insight, but it's a pity that very rarely we can use it to validate our model, and we have to produce more data for that.
I think that's something that the community is understanding. In Europe, we have ICOs, urban ICOs, developing, deploying urban observatories to generate this type of information. And in the States, in North America, we have Flux and the Department of Energy supporting this kind of observatories in a number of cities to produce the data that you need as.
I know, but when you try to use it, they forgot to measure something.
I guess we have to work together, experimentalists and modelers.
Yeah, we need both.
Yeah.
Thank you.
Thank you. Yeah.
I have a question regarding the age of trees that you used as one of the parameters in CFD. So does age reflect only in the size of the foliage or also the physics?
Oh no, the physics for the very, very young tree, is still flexible, okay, so that the trunk can still is not the same solid structure. So it is at one point you get, so from a sapling to a young tree, you have much more deformation. And at one point, the trunk becomes very solid and almost like it has to take over, it becomes a more static structure, although it's still oscillating. So in terms of the mechanical way the tree evolves, it's different. The physics of the photosynthesis is not really different. The leaves are the same. The leaves have, maybe a young tree have smaller leaves, but soon it will be the same leaf size, whatever the age of the tree. You will have, of course, the center for a big, you don't have the same distribution of leaves. A big tree, a very old tree has more, really the leaves that are more because it's a bigger volume, has more leaves outside, and the center is more occupied by big branches that have a big structural load to take this load of all this big weight of the foliage. A younger tree has more leaves even in the middle. So this, that in the physiology of the tree with age, there's a small change of distribution. Yeah.
So in CFD, it's only the size.
Sorry?
In the CFD modeling that you.
Different size.
So the size here, so we can change the foliage distribution in the volume to represent the age of the tree. Then we can also change the LAD, so the leaf area density everywhere. We can change the coefficients for the size of leaves that we can change. The stomatal resistance, it can be calculated or we can change. We have also the extension coefficient, how much the solar radiation is attenuated by the leaves.
In Singapore, the tree actually grow faster in tropical areas. So when we make decision what tree species we should introduce into the urban areas, do we need to run a distribution on 5 years old and 10 years old or 20 years old?
Well, 5 years old, it's not useful.
Just for example.
They are so small, they don't have a big impact.
I always want to try to save some time for the designers and urban planners. Yeah. Is that possible to provide some data set so that they can use as the reference to check, okay, so what's the impact after they grow up?
Well, eventually, yes. Yeah. Now we don't have such what we know. So we know the size of the tree for age, depending on the climate for different species.
Kind of amateur study, we provide the data.
Yeah, so the big data set for age of tree and size of tree is called I-tree.
Oh, okay.
Okay, that's so far the best data set for trees.
Oh, okay.
Maybe I can ask questions. Thank you very much for these inspiring lectures. I am really amazed for everything. I have been working on the multiscale environmental analysis tool during my PhD and during my postdoc. And along the way, I used and tried to learn different tools. So you mentioned that you use hybrid methodologies to, achieve this point. I want to ask, what was the most challenging point along these methodologies? Because I did field experiments too, I did simulations too, and I just wonder your point of view on this.
So I think that just to understand, to discover, there was always something else too. There's always something missing. We should include that. We should include that. We always have to add something.
So I think something what is very challenging is that at a given moment in your career, you have to decide, I will do this, right? So somewhere we decided to develop all these kind of models. For that, you need funding, you need people. Somewhere you have, of course, consortia, like for instance, Paul, more than 30 people are working on everything together. There are others, of course. And so as a small group with not so many people working on that, you have to be sure that what you are doing is a good way of doing, and of course going in all those details, physical details, whatever. Now we started in 2008 where not a lot of people, we started finally in 2000, okay, with CFD and Drive Away. At that moment, we got the time to develop all those models, and now we are ready to do, as we have seen, quite some simulations. Now, what I find still a challenge is to convince people to use such a kind of model that is quite complex, where you have to understand all the physics, while you have also maybe very easy models where you have not understand how to make a good measure in CFD. They do it for you, but I find this a challenge to convince people that you should go to the what we call the all physics modeling. I think that this is something now that people really try to bypass. Of course, these simulations, of course, need supercomputers, and you have also to convince people that although you use supercomputers with maybe a big carbon footprint, this is worthwhile doing. So this is a challenge, I find, to give people the time to develop tools that are open, or they can always be improved in any aspect, and that's also why we do it open source. So it's open source; everybody can download it and look at it. So that's for me the biggest challenge.
Thank you very much for sharing your experience.
I would add that when Jan started, so he started before me. When he started with CFD, he was accused by one of his colleague professor, why you use a bazooka to shoot a fly? Because there was it was for this professor in building, it was so stupid to use CFD when you're in building. It should be just mechanical engineers that do that. Okay, so it was really like and then after that, the jokes for many years were you don't do computational fluid dynamics, you do colorful fluid dynamics. It means nothing. It's not validated. So a lot of critics like, why you do these complex things? Then at one point, people started to say, oh, it's nice. Okay, we can, but it's too complex. It's nice for you, not for me. It's too complex for me. And then you started to have after that the easier tools. And then people say, well, okay, you do that, it's nice, I will also do it, but I don't want to learn the physics, I don't want just want to click a few buttons. So there was always there's always a tendency for people to look at what we do. It's too complex, so it's not for me. When actually you can get a real mastery of what you're working with. Of course, it's a big investment, but after that, you really understand. You can really explain what you do. You're at a position of expertise and knowledge that almost nobody has. So, of course, you have to learn. So now we are 60. Okay, we are still learning all the time. It's not like some people think they will learn everything in the PhD and after that they don't learn. No, it's not true. We are still learning all the time. There are still things we say, how we will model that, what is the approach, what is this thing? So we are looking at a lot of physical phenomena that we do with other type of modeling that gives us insight after that. So it is interesting. You have to find that it's interesting to learn, and to learn you need to develop something, and then you do it because you want to understand something better. You don't do it because you want to be the best in the world. It's not that. It's totally different.
I would like to follow up your answers. So 10 years ago, 20 years ago, we tried to bridge the gap between the urban modeling, climate modeling, and the urban planning practice. So now we are trying to introduce the urban modeling to more stakeholders. Yeah, so we always said that urban planners need to learn, all right? So now we are facing maybe more stakeholders, and we are trying to introduce the modeling tools to different stakeholders. And what's the challenges? And what's your suggestion to bridge more gaps?
So I think in the design process, you need a lot of different stakeholders.
Yeah.
For sure, not only the academic people, but also not only the urban people, and not only
the architect,
or not only the architects or the owners, but also the inhabitants.
Yeah.
If you, as I try to explain, if you have to adapt and mitigate, acceptability is very important. So people have to accept. So I find that one of the stakeholders that really have to be involved are the inhabitants. And it's not only that we have to learn them what to do, but they have also to learn us what is possible. So I think this is the big framework. But somewhere you need, of course, also experts that can somewhere have some input, so that if suggestions are done by inhabitants or other people, that eventually you can evaluate that. And as I tried also to explain, is the assessment of one mitigation measure is, of course, not only on comfort. It is it can be energy, it can be a lot of things. So I think in addition to what we do, you need to establish, of course, a big platform. And I know, I see a lot of colleagues that have just these kinds of platforms which are visible, and where maybe very fast stakeholders can do something with it and learn what it can impact. So I did not say that this is the model you have to use in the design, in the urban design, but you need a high-level reference model. That is the reference. I will say that this is the reference, but somewhere, if you make simplified models, machine learning models, you need somewhere a reference model that is validated, which is maybe quite demanding. So we don't say that you have to use these models in design, although, as Dominic showed, we did it with stakeholders. We do it with the city of Zurich, and it took me 10 years to get a good relation with the city of Zurich and the city of Genève. But now they come to us. If they have a specific problem, they come to us. And of course, what we give to them is not a model and all the results. We give some guidelines, we give some knowledge, some knowledge transfer. But the city of Zurich never asked us to have a tool to do it themselves. So I think we should not totally replace everything by tools that everybody can use. So I think everybody has to have his role in this very complex decision process, right? Okay.
Just if, like, I don't know, in Canada, in building design, now you always have a specialist that do building energy simulation. Okay, like 20 years ago, it was totally crazy to do that, but now it's part of the design process. You have, it's not the mechanical engineer, it's not the architect, it is a specialist. So there's a new specialist that does simulation that support the design.
Yeah.
So you eventually maybe you will have another type of specialist at urban planner around the urban planning table.
Yeah.
Okay, thank you. I saw there's the question. Yeah.
So you mentioned the figure of about 2 degrees. That was the mitigation target. For solutions, I imagine that is a very sensitive amount. It depends where the city is and things like that. And so I was wondering if you want to comment on like how much this target can change from place to place, and how you'd start thinking about the problem of mitigation when this target is, when local measures simply are inadequate to rising temperatures.
So this is when we measured the 2 degrees, it was air temperature that you can decrease by, but you can do a lot in terms of shading to decrease by 20 degrees the surface temperatures. So, and then you can also play with evapotranspirative cooling, so certainly like using water, like the latent heat of water to cool surfaces also. At the end, I don't think you can ever succeed in really mitigating the urban climate with only one measure.
So, and of course, the question is, what is your reference? If you say there are no trees at all, and I start to put trees, of course you will see quite some effect. What I was meaning is you have already a current situation and you want to optimize it. You want to add some things, and as in the examples I have shown, there are some situations where the air temperature you decrease is quite limited. And one of the reasons, of course, is because the heat capacity of air is very little. So physically, to cool air, it's very difficult, right? Or you need to have really very low temperatures to cool. So a tree is not cool enough to cool the air temperature so low. That means that people still use air temperature much too much as the metric to look at efficiency of mitigation measures. What I try to show, or what we try to show here, is that using a comfort index, whatever it is already much better, right? And there, the main aim to me is not to say, okay, I will propose you a measure that all time will decrease the UTCI with 4 to 6 degrees. It's impossible to say. But you could, of course, make, for instance, that people that are in an environment which is quite hot, that they have a path to access, for instance, a river or a forest in a distance that is, in the future, affordable to do. So I think you have to think that way. So to think in absolute terms of we will cool everything so much and we will do this, I think this is, you have to think this as solutions that make that people can live in a changing climate. So maybe it can also be that we have to say to people, you have to change your thinking. What is suffering? I know a lot of people that the moment it's hot, they say, oh, we have to install active cooling. In Montreal, in Belgium, it's like that. Heat wave, oh, we have to do something. Where I say, no, why you did not think of installing already heat pump or whatever solution? So this is the mindset. So people are very sensitive at the moment of the problem, and then 2 months later they forget. So this is that's, I think, the solution is adaptation, mitigation together, and just don't tell to people, I can give you a technological solution that can solve everything. Yeah, that's active cooling and stay inside, but we know this is not a solution. Right?
Thank you.
Why do you models actually as closed media? Closed media access point, I mean, just point the velocity. Then how about the real-time local effect of the wind as it passes the tree?
How about the what?
The wind as it passes the tree. Because when we model it as a porous media, then it will just have a drop in velocity, and it won't have a change in the direction of the wind as it passes over the tree. So how to take it upon?
So if the question says how the wind can go through the foliage and still be accurately modeled,
how it can replicate the tree in reality?
because we put the density of leaves in each mesh of the system of the CFD, and then you put a drag coefficient there of the leaf, so that you can have you just reduce the velocity and the momentum of the leaf of the airflow depending on the density the density of the leaf in each volume.
So you introduce, so you have a tree, you divide it in cells. In every cell, you add a sink or source term to mimic what the porous medium does with respect to the momentum, the mass conservation and everything. So you change all the equations one by one. And then you say, oh, now I know in one cell what is my relative humidity or vapor pressure. I know my temperature. I put there now a leaf. And for that leaf, I calculate a heat and moisture balance. And this leaf, of course, is connected to branches and whatever. So you can all model this as a network. So another approach is where you model every leaf. And you have a discrete approach where you model, and people did that, modeled really the flow around all these things. This is too expensive if you want to do one of these. So that's why you use this porous medium approach. But behind this porous medium approach, you have what we call a multiscale model that goes to the leaf level. And so you calculate the second balance for every leaf. And eventually, balance for the moisture flow in your tree.
The question is about how about the change in the wind direction as the wind passes over the tree. It will have some small diversions. But when
so you have
the porous media just passes through it.
Well, it passes through it, but there's also you calculate the flow. So if the depending on the shape of the foliage, and then you have if there's walls and all, so the wind will go faster. There will be some turbulence, so you just calculate it. It's just a normal safety calculation with some cells. There are some resistance because of the presence of leaf that reduce the speed and the momentum.
Maybe, I would like to say maybe your answer scared the landscape architect. You mentioned the momentum, and they will say that I cannot control the individual leaf, okay? Basically, I just want to make decision on the form of the tree crown. And so my question is that what's the reasonable way to simplify the modeling and to help them make the accurate enough decision?
I think the answer is if a landscape architect wants to understand exactly what is the role of
they want
tree,
to learn but cannot learn so much. But they still want to apply this, and
they just work in a multidisciplinary team with somebody that is doing the modeling. And they exchange information like that. So you don't need all the members of the design team to do the modeling.
So maybe I can answer also the question by making comparison with wind comfort, which is already there for 30 years. There are standards how you have to do it, how you have to assess it, evaluate. We are far from that. So there's no. Everybody is using his own
comfort index and says how much you have to do, whatever. For wind comfort, it's there. What do people now do is in a lot of countries, if you have a complex building, you have or to do a wind tunnel study, or you have to do a CFD study. There's no way out.
Okay.
Okay. So you have companies that do that for you.
Hire the consultant.
Yes.
The consultant.
Yes.
Oh, okay.
And the consultant now, what he does, a good consultant, what he does, he does a two-step approach. You come to the consultant and say, I want to make this building. And he says, I give you a first advice based on expertise, machine learning, whatever. And you already say, okay, these are the problems, these are the solutions. If the client says, I'm okay with that, I don't need more, okay. But if he says, I need more, then you do a CFD calculation where the initialization is again based on machine learning. So they have a database of problems. And so they know exactly almost how to solve a problem that looks alike. So I think that's the way to go.
To come to that.
So, but that means you need a consultant. If you want to design a building with a very, even this floor here, you go to a structural engineer, right? To say how to do it.
It's not the architect.
You don't go to the architect to say how I should. So even famous architects like Calatrava, he calculates everything, or he lets it calculate.
But he's a structural engineer.
He's a structural engineer, right? Yeah. But so why we want to avoid? But I say I agree with you. You have not to calculate everything with brute power. No. So if you understand something, you can design with design rules also. But there's a step approach. First step, maybe 90% of the solutions you can
evaluation at different stages.
But the 10% which is specific, where you don't know the answer, you should just simulate it, right?
Okay. Thank you.
There's a question on Zoom. Is there scope to study the empirical data of before and after the design intervention to further refine the model?
So you mean to use like so that you could use actual cases to compare with modeling? Of course, when people would provide such data, I'm sure we would use it. Yeah, there's almost no urban climate complete set of data now where we can compare everything.
Yeah. So I think what we focus too much on is the design, but we are not looking at the assessment or the impact assessment after 20 years. And of course, this is very important information because that can say us where we were wrong or where we were correct or why we were wrong. Or why it did not work, why we decided to make there an urban forest and people don't go there. Why? So, of course, I think there's a lot to be done after the design. It's the commission of a building, right? You want to know after 1 year if it works, but maybe in urban design you need to wait 20 years to know what you designed is correct, right?
That may be too long.
In Singapore, for 20 years, the building might be not.
Oh, yes, of course, yeah.
So the urban planners need to wait 20 years to see whether their strategies work or not.
Not for that specific case, but you can learn out of it a lot.
Yes.
Remaining within the realm of process-based physics models, many of the simulation here, especially when we go to the 3D landscape and resolving explicitly the geometry and the spatial domain, they are very computationally intensive, which implies you can run maybe a few days, what you were mentioning before, or maybe one typical day, or even one specific hours or some time. While certain type of problems, it's better to have a longer term perspective, and there are other type of approaches which simplify the geometry, but they can run on a longer scale, of course, coming with pros and cons. What's your feeling or opinion or judgment between these trade-off that has to be made?
Difficult question.
Yeah, I think we are still trying to understand like how to do very, very well all the explicit modeling for a certain type of week or 2 weeks time. To what level we have to do, what we have to include, how much of. So I think the tool is still being developed. There are some aspects we are still developing, but it's quite complete. And now we are really doing a lot of trying to use it to understand everything we can do, or how much we can do for studies that are, of course, just 1 week or 2 weeks or 3 weeks. So that and after that, to see the amount of information we can get, what is the most relevant information. So now we are focused on going to a heat wave. So this was the main impact. So the other type of study to look at what is happening for the whole year in terms of the climate and all that, we could still do this. With this, we can look at another 2 weeks in the year. We don't need to we don't need to do 365 days. We can still look at different conditions in the year. If we wanted to do a more full year simulation, it would not have the same level of information.
So it depends on for what you are designing. Yeah? If you are designing for extreme events like a flood or whatever, it's a different design. So if you look for building energy, for instance, you can say I design the cooling or heating system, then you look at extremes. But if you say, oh, I want to know the complete heat demand over a year, of course you need other tools to do that. Right? So what we were talking here was really the design for extreme events. And what you can do is, of course, you can say, I go for future events looking at some CO2 emission scenario and try to predict. Now, what we know, and that's the same problem a little bit, we can predict, given some CO2 emission scenario, what will happen in the future. But we cannot predict extreme events at all. So that means, how do you then design for an extreme event? You take the 2003 heat wave, because you know and you have all the data. So you are well informed how to do. So this is what they call the what-if design strategy. You could say, I take an extreme heat wave, I don't know, in another country. I think that, for instance, Spain, and I think that in 20 years, the heat wave that happens in Madrid will happen in Zurich, and I designed for that. Then you don't have to run 30 years or 1 year or whatever. So this is it's a design for the extremes, and that's what we presented. Of course, if you want to know what is the climate, like they do also in energy demand, you go to typical days. You have this rolling horizon, a lot of numerical techniques to speed up. And so I'm totally not against that. But it's another question, right? And you can have parametric models like you use, of course. So I don't exclude one from the other. This is a model where you would do the all physics because you want to calculate on a short time what the extreme does.
We still have time. One more question. Okay, so.
So we'll be closing the event. Thank you everyone for participating with your questions. We would also like to thank Prof. Dominique and Prof. Jan for sharing their really insightful work, as well as Prof. Yunchao for moderating this event. I'm sure we've learned a lot. Thank you everyone for attending this event and actively participating with all your questions. We are also pleased to inform you about our next lecture on 19th of December by Mr. John Kirker. He's the Senior Urban Development Specialist with the World Bank's Sustainable Development Practice Group. Do register for the same at the earliest. Please also watch out for our social media channels as well as your emails for all our future initiatives. Thank you and have a good night.